Welcome back. So, in our last lecture, we looked at the similarity parameters and ways to derive it, and we actually saw how we derived the let me go up the drag equation which we had derived for a body which is immersed in a fluid, in an incompressible fluid, and the body in this case was a sphere, right? So we did that, and in a similar way today we are going to see how we can do that and derive different equations for a ship using the governing equations and certain boundary conditions. So the similarity parameters are actually obtained by scaling and non-dimensionalizing. Of course, we have done the non-dimensionalization in our last lecture as well. So we find out the similarity parameters by scaling and non-dimensionalizing the governing equations or the boundary conditions. So what do we mean by scaling first of all? So suppose we have velocity as a function of space and time, okay? And let's say that at any point in space of time, the magnitude of this velocity equals to alpha times some constant velocity which we have. So it's alpha is a constant and u is the magnitude. So this is of course dimensionless. If this is the case, then we can write velocity as capital U times v star. And what is v star here? V star is the normalized velocity which is dimensionless. So v star is dimensionless and it's normalized, which means its magnitude is kind of 1. It's normalized. So we can write v as capital U times v vector v star, and in a similar way we can write this for other characteristics also. For example, we have this table over here. So for velocity we had the dimensionless normalized quantity as v star. In a similar way we can have for length as x vector star, and therefore you write x as capital L into x into star. So your L, U, T are nothing but kind of dimensionless counterparts of velocity, length and time respectively. Similarly for pressure we have the same. Okay, so we have now derived the dimensionless and normalized counterparts of velocity, length, time and pressure. Now what we are going to do is we will substitute these into let's say the Navier-Stokes momentum equation. So we had the Navier-Stokes momentum equation as, let me just quickly copy that as well. So we have the Navier-Stokes momentum equation as this, and now what we are going to do is we are going to substitute the above quantities into this Navier-Stokes equation, which was for the momentum Navier-Stokes equation, and we are going to get something like this. So we have nothing but we have substituted for v as u into v star and d by dt, so divide that by t, for normalizing the derivatives as well, because del by del t will also be kind of a function of time, and we want to normalize and scale that as well, and therefore we'll have it as u by t del v star by del t star. In a similar way we have substituted for all of them from this above table, and we have got something like this. So in this equation, u by t u square L into this, and rho naught minus rho v by rho u square, rho nu u by L square, these are all what? These are all dimensionless quantities. So we can actually let me just add a tilde over these quantities, and these are all the dimensionless quantities. These are the coefficients and these are the similarity parameters. So that's it. We just derived different kinds of dimensionless quantity. For example, if we take the first one, so before doing that, actually we are going to divide all of them by u square by L, to just as a convention method, and we are going to get something like this. So this is nothing but dividing this equation. So we just divide by u square by L order of magnitude of the convective inertia term. The convective inertia, and we got this, and the tilde is already added. So these are the similarity parameters. So if we look at the first similarity parameter, which is L by ut, this is called as the Strouhal number. All right, and this is nothing but this is kind of the oil ratio between the Eulerian inertia and the convective inertia. So we have talked about the convective derivative or the material derivative, so that's where it comes from, Eulerian inertia by the convective inertia, and this I can write down as del V by del T divided by V dot del into capital V. These are the convective inertia terms which we had seen. And suppose, let's say your ship has been traveling for a long time, and the total time it takes to travel, the length of the ship is, let's say, some t, which is not capital T. So if t is much larger, which is capital T, is much larger than the time required to travel the ship. So let's say you have a ship like this, and its length is L, and the time required to travel from this point to this point is, let's say, small t. If capital T is much greater than small t, then what we can say is we can assume that the ship has reached steady state, which would mean that L by U is much less than t, because at the end, if you see, if U is the velocity, L is the length of the ship, L by U will give you the time taken to travel from one end of the ship to the other end of the ship, right? It's the distance divided by time. So now what we have is L by U is much less than t, and this we can write as the Strouhal number. So this is much less than 1, and therefore we can simply ignore this quantity in the Navier-Stokes equation. We can simply ignore it. So that, assuming steady state, so that simplifies a lot of our problems, right? If we can simply ignore this term over here, we can simply remove it out, and that really simplifies our equation which we have to solve. So as you can already see that similarity parameters and ratios can help us to, really practically solve our problems easily. In a similar way, you have other parameters. For example, if we take this one, so this is known as the cavitation equation, which I'll just write down again. So it's rho naught minus rho v by half rho u square, denoted by sigma, and this is known as the cavitation number. Now cavitation is a term which not always, but happens in propellers which are rotating. So due to pressure differences, bubbles are formed at the surface of the propellers, which actually corrode the propellers and take out the material. So that is the cavitation, and therefore you can predict the cavitation happening from this equation, and you can also have some other assumptions from this equation, and so on. You have a lot of different ratios which we derived from this, and I'll just actually present a table for these, all the ratios which we have and all the similarity parameters which we used in marine hydrodynamics. Now this is not an exhaustive one, there could be other similarity parameters as well, but these are the main ones. So we have the Reynolds number, which is velocity into length by viscosity, so which is a ratio of inertia by viscous force. Froude number is a ratio of inertia by gravity. Similarly, we have Euler number, cavitation number, Strouhal number, and Weber number. So whenever you are designing a ship, you have to take the similarity parameters into consideration, so that you actually simulate the actual ship, the actual large scale model ship which you will be building. So these are the similarity parameters, and of course you now know their importance, how they help us to practically solve an engineering problem and to scale down a really huge ship into a small one for practical experimentations in labs. So that's it for the similarity parameters. See you in the next lecture. Till then, stay safe and thank you.